that ring on a imidazole, that's right. So it's an imidazole ring. So what it turns out is that imidazole ring, we have 6 histidines like this. It binds nickel very well. So you basically, I'm not going to draw all those, all that. Basically, all those his around there, you can basically go in 3 dimensions. All those his around there chelate nickel very well. So the his tag chelates nickel. So now we have our stationary phase. It's modified in a way that it actually binds nickel. So we basically have nickel 2 plus chelated onto the stationary phase. Now, say we use E. coli as our protein expression system. Okay, so we've basically taken an E. coli, we put in that speculative plasmid so that it contains their gene of interest, except we've actually modified our gene of interest, so when it makes the protein, at the end of the protein, it actually has these extra 6 histidines. Now, also in that E. coli are all the other E. coli proteins, the other 3,000 or 4,000 or whatever it is, E. coli proteins. But none of them actually have this 6 histidines in a row. To get 6 histidines in a row is rare. It would be highly rare. I could probably calculate the probability of having a protein with 6 histidines in a row just by accident, but it's pretty low. Okay. So now what happens is we've got our protein of interest with the 6S tags. We've got all the other non-tagged proteins. We flow these proteins through here, and the non-his tagged proteins flow through, and then the 6X his tag proteins bind the nickel. All right, so now we've basically taken our, here's our non-his tag protein. What's nice about this is now we've separated our protein of interest from all those other non-tagged proteins that are in E. coli that are just needed for the growth and so the now question is, how do you elute? And you elute with high concentrations of imidazole. Again, that's that ring structure on its own side chain like that. And that basically outcompetes the his tag for the day. And this works pretty slick. You can also do things like drop the pH to elute, because it turns out that the imidazole has to be deprotonated. So if you drop the pH, so it just becomes protonated, positive charge, and no longer binds to the nickel. The problem with dropping pH is sometimes you mess up the protein structure, and there's some other problems associated. was typically done just by increasing the invisible concentration. All right. So we've gone through these four different methods, ion exchange, side exclusion chromatography, hydrophobic interaction chromatography, and affinity chromatography. And I've drawn these sorts of chromatograms, at least for some of those, when we talk about protein concentration. Now what I want to do is talk about a little bit about the third thing we have to do is how do we actually measure the protein concentration? So this is we're detecting the protein of interest. Well, the first thing we can do is detect total protein. That's how I covered it up, I guess. But that's basically what we're doing here. We're detecting any protein that's coming out, okay? And the easiest is this. We can measure the absorbance at 280 nanometers. Because there is if we look at a UV vis spectrum, absorbance versus wavelength down here, we start down like 180 or so, maybe 400 nanometers. A typical protein spectrum absorbs a lot down at 180 to 200, and that's due to the peptide bond. Then it basically comes up and has a peak at about 280 nanometers. I didn't put the 400 out. This is due to aromatic amino acids. And really, what are the three aromatic amino acids? Tyrosine, tryptophan, and phenylalanine, right? And so this is really mostly tryptophan and tyrosine. Now, you say, well, why don't we just go down here to 200 and just measure where the peptide bonds are? Because there are lots of peptide bonds in a protein, right? The problem is, if you get down that low, and almost everything absorbs down there. So anything in your buffer and all that sort of stuff is going to be down there, and it's not going to be very selective for protein. And so you come out here, and that gets you away from the absorbance of buffer components and that kind of thing. It comes up here that 280. Let me show you, we'll get finished up here, but we'll show you a couple of slides. So here's the absorbance spectra of three different aromatic amino acids. Again, we've got wavelengths over here. We've got the absorbance over there on the left. We basically see, and this is sort of at equal concentration amount. The thing that absorbs the most is tryptophan, and tyrosine, and phenylalanine. Phenylalanine is a peak a little bit closer to 260. Tyrosine is around 280. Tryptophan is a little bit shifted, redshifted relative to tyrosine. we put these together, you know, if you have a protein that has 100 or 200 amino acids, it's likely to have at least a half a dozen of these. Okay, and so total UV spectrum looks like this. And so we basically come up here, here's our peak at 280. This little hump here, that's known as the tryptophan shoulder. That's because that tryptophan is slightly red shifted. So that little extra is due to the tryptophan in particular. Now, what's one of the drawbacks about this method? What do you need for this method to work to be able to detect a protein? What's that? You need to have the aromatic amino acids. That's right. So if you have a protein that doesn't have any aromatic amino acids, it's not going to be any good. And we throw that in 162. They're still doing that with the protein color. So that's one of the limitations. Okay, we'll stop there. We'll finish up.